guess there's not really anything to start because we're already started.
Yeah.
All right, everyone, welcome to Networking for Server Admins. I am struggling with PowerPoint. I'm Matt Cozzolino. I've been a VCP for a handful of years now. I've been working with VMware basically my entire professional life. Everywhere I've been as a IT administrator, I've been using VMware. In general, I like VMware because it's really actually fairly mature. They've got some cool virtual networking products. They've got some portability stuff. I find it to be a really, really neat product. In general, I like to learn something and I like to pass some knowledge on kind of every day. I do that in a couple of different ways. When I'm not here working a desk doing computer stuff, I do ski patrol during the winters. So that's my other avenue of learning and teaching and whatnot. With me today,
Jeremy Goosen. So I've been in IT for quite a long time, as you can see, and 14 years as a consultant, mainly on the networking side. I have miscellaneous Cisco certifications, Guardicore Akamai, and other network related certs. Outside of technology, I do lots of DIY work around the house. I'm in the middle of several huge projects at the moment. So yeah, that's me.
sweet. And for everyone that's in here, we do have a Q&A session that you can see in part of the Zoom. So there's a raise your hand, ask a question. Please do that. It's way more fun to answer questions and talk about things that have real world impact for you than it is to just go through all of these slides and talk about the networking piece. So please ask questions. As we go through this, we're going to talk about some kind of network fundamentals, and we'll try to bring it to what you as a server admin or network or a storage admin or whatever other not network admin will need to know or should know about the networking piece as you're interacting with the network team. So we've got some kind of general topics. We've got a couple of not case studies, but like I have a thing like a new ESXi host or a storage array that I'm going to deploy. What kind of questions do we have to go through? What's that workflow look like? So yeah, we'll kind of pose that in a what kind of question should you ask? How does a network engineer approach the problem? Because that's oftentimes different than a server admin. And kind of get into some of the things like why is this what I think should be a simple question super complicated and way more complicated than it might look, than it might be, than you might expect. So without further ado, let's
Yes,
talk.
don't panic.
Let's talk about some different networking concepts first and kind of set the stage and talk about some stuff here. So in networking, PowerPoint. In networking, we've got this broad concept of layer 2 connectivity versus layer 3 connectivity. Layer 2 connectivity, I've got an analogy. It's like a bar. You're in a room, everyone's in the same room, you can talk to each other. There's no security between layer 2. So if you're standing right next to someone in the same room, there's nothing to prevent you guys from talking to each other or interacting with each other. So there's not a security type device. Communication on layer 2 happens via the MAC address. That's also kind of where the default gateway lives. When we start talking about layer 3, we're talking about how to connect those things together. That's how we get to everyone else. There is a ARP and a broadcasting that we'll talk about in a little bit that covers that layer 2, layer 3 kind of change between them. But I'm a huge fan of pictures and analogies with stuff. So when I say layer 2, layer 3, layer 3 is giving me my driving directions. Each intersection is kind of a router, a layer 3 device. So I use these directions to get from point A to point B. So that's my layer 3 pathing. That's my routing. That's my dynamic routing piece. And then when I get there, I got to get past the bouncer, get past the security device to be able to get into the bar, right? So that's my layer 3 piece. And conversely, we're inside of the bar now, and everyone's right next to each other, shoulder to shoulder. There's no security inside of that. So that's kind of a big concept between layer 2, layer 3. if you keep that going and use that analogy, we can talk about things like why is it not a good idea to have two bars connected by I want to say like a hallway, but like if you've got two different environments, two different data centers, why don't you want that all to be one bar? You kind of want to have one that you can open and close and another one that you can open and close. And maybe there's a way to connect them with a router or something. Jeremy, any thoughts on that? Anything you want to add to that?
No, just don't spread layer two too far.
Right. Make it consumable, make it scoped appropriately. This is your layer 2 domain. It exists on a single set of equipment. It supports this set of equipment, and to get somewhere else, I route is a preference to do that. One of the things that we want to prevent in that kind of conversation of, why do we have connectivity between these two different sites, is there's a lot of other traffic that we generate on the network. There's ARP traffic, there's broadcast traffic, that's the FFFF. There's ARP tables, so you can look up your MAC address along your IP address. We're doing gratuitous ARPs. All of that is just that background noise that's happening in that room as all of these devices are talking to each other. And if you've got an even bigger device, everyone's been in a giant conference hall or expo hall or something, and there's that echo and it's loud and it's just so much noise. That's the kind of thing. That's one of the things we're looking at preventing when we don't do layer 2 stretch networks between the environments. Let's see. So other kind of related. NSX, I mentioned earlier that there's a virtualized networking component. NSX handles these ARP broadcasts and broadcast components by being able to update smartly the information about those networks across end to end. So we don't have to do as much broadcasting because all of the VMs in a virtualized environment, we know the MAC addresses, we know the IP addresses, so we can answer those questions without having to say, hey, who owns this address? Some other things, some other kind of networking basic concepts here is the difference between TCP and UDP. I'm sure a lot of y'all have seen this before. TCP is what we call a stateful transaction, right? Or a stateful connection. We're saying, hey, I'm going to give you this package. Would you like this package? Jeremy, do you want this package?
I got the package.
Cool. Thank you. I gave you the package. Awesome. And UDP, conversely, is like, yo, I tossed this thing in your front yard. Have fun. Peace out. Right? So there's a connection there. We hand it off nicely. UDP is, I kind of hope you get it, maybe. So let's go on to some addressing. So we've got a question for you here. We've got a poll to put up. Awesome. Let's give you guys a second to answer those. This is where we need that music. Yeah.
Yeah. Ah.
Cool. And then we do that so you can. Okay, there we go. Jimmy did it. So it's kind of a trick question, kind of a let's see where you are, see what we're thinking about stuff. Classful addressing. Okay, there we go. Yeah, click the buttons. So it's kind of a loaded question in that none of the above is the appropriate answer because classful addressing doesn't actually work anymore. We do not use that anywhere. We stopped using it in 1993 with RFC 791. I bring that up just because I've got, I usually grumble, shake my fist at that when I hear it. But if we want to be super picky about it, the first octet is what defined the class. So 10 dot anything technically falls in a class A network, and 128 through 191 technically falls in a class B network, and 192 through 223 technically falls in a class C network. That /24 at the end had nothing to do with classful networking when we used it. but at the same time, we don't actually use it at all anymore. So there is no such thing as a Class A, Class B, Class C network in today's world. Instead, we use CIDR addressing, classless interdomain routing. That's where we get our /24s, our /30s. When we do that, we define a network. We get the network address. In this case, it's a .0. We get a broadcast address, in this case, .255, and then a usable range between them, .1 through .254. Fun thing with a .31, there's only two addresses. The network and the broadcast kind of also are the two devices that you can assign. You can use a /31 for routed links and stuff like that. So know that private address, that CIDR is what we're using. Don't ever say classful and you'll get extra bonus points whenever we talk. Yeah. Thoughts on that, Jeremy?
Yeah, no, just keep everything, it's best to keep everything, in its own lane. Small /24s, subnet out throughout your network.
Yeah.
No supernets.
No supernet. Sometimes it makes sense to grab a chunk of addressing and carve it up for a location so you can have a single route.
That makes your life so much easier.
Yeah, there's some planning that you can go into. That's that whole layer 3 design. That's what kind of the network team is fundamentally thinking about, is like, how do I get these addresses, or how do I assign addresses to all the different components in my environment? How do I make sure that they're secure and route between them? Using that most of the time, unless you're super awesome and using IPv6, which I will say I am not at all right now. For the most part, everyone's experienced the RFC 1918 addresses. These are the private address space. Every time I do a firewall update, when they're talking about stuff, I know Jeremy does the same thing. I make 4 addresses and put them into a group. I've got RFC 1918 10, RFC 1918 172, and 192, and then I'll take those objects and group them together in a single RFC 1918 object. So I can do things like, if I'm sending traffic destined for 10 dot something out my firewall interface, I can decide to just throw it away because there is no 10 dot something out on the public internet. So you can do stuff like that. Thoughts on that, Jeremy? I know you said you do the same kind of objects.
It's the exact same thing I do. On every firewall I touch, you'll see these. You'll see an entry for this. And it's usually pointing down to the core. But yeah.
Yep. And you can, we all do it. We've all probably got probably a 192 address at home. We can use any of these anywhere we want inside of our own network, and then do some natting on the outside to get to the public internet. So all of those, that private address space, that CIDR notation, we put all of those together, we make some definitions, and we define a VLAN, or a network segment. We define a number for the VLAN, and we define a subnet to apply and use on that VLAN. There's some weird things we can do there that we don't necessarily want to, like have 2 different subnets on a single VLAN. Not necessarily the best thing to do. Sometimes there's a need for that. Shouldn't be doing it, but sometimes there's a need for that. But that brings us to this concept of a VLAN. It's not really a magical anything. It is just a construct to contain traffic. So this is that definition of the bar. This switch 10, switch 20, switch 30, that is the one bar down the street, the bar in between, and then the other, the coffee shop right next door, right? Those are 3 independent environments, 3 independent VLANs, 3 independent segments. You can look at them and think of them as their own little switching infrastructure. The thing that a VLAN does when we define it on a switch is it gives us manageability of it. So we can have multiple VLANs exist inside of the switch. Fundamentally, they still work like that. You can't get from VLAN 10 to VLAN 20 because there is no connection between them. The things that connect VLAN 10 and VLAN 20 are a router, another layer 3 device, another layer 3 device, right?
Yep.
So that brings us to, how do I end up connecting to this switch? So if we've got over, let me do a little doodad here. So if we've got over here on VLAN 10, we've got our wireless access point and a tablet or something connected. How do I connect this device, this access point, into this switch on this switch port? I have to do some configuration of the switch port here, or in this instance, Jeremy would have to do that. Maybe I've got a couple of devices. Maybe I've got a phone and printer, or a printer and a workstation on VLAN 20 and a couple of servers on VLAN 10. So what kind of connectivity are those? Jeremy, you're creating something in either access port or trunk port, right?
Yeah, access ports or trunk ports. If you're going to have more than one VLAN cross an interface, it's going to be a trunk port. If you're going to have a single VLAN, it's going to be an access port. And so this comes back to, is this a single device? Is it a server? Is it an end user computer? If you have to set up like to where the phone connects and then the computer connects behind it, that's actually a trunk port where you get to play with something, a concept called a native VLAN, to where you have like the native VLAN, which is considered like the voice VLAN. Or it all depends on how you're set up. But usually with the servers and the data center, you're going to be setting up mainly .1Q trunks. If you need your management interface to be the native VLAN, so then that way when the device comes up, it basically it comes through with tagged and untagged VLANs. Or native VLAN, depending on the devices that you're working on. Tagged and untagged is kind of the common way to talk about it. But the native VLAN, when you connect that up, that's what the device will think is an access port and come up on like a VLAN 0. And then anything else that you want to tag as far as traffic wise, you would tag that VLAN. So it'd be VLAN 15, 16, 17, your server network, your storage network, and your data network. And keep management as a native.
Yeah. So if you think about that, and we come back to some analogies here, this is a paved road and this is a paved road, right? This has one lane and there's only one type of whatever you put down this traffic, whatever drives down this road is going to drive down that road. And it's all driving down the same road, driving down the same lane on the same set of asphalt. Here, we have the same set of asphalt, right? There's one cable, but we have a space for autos, a space for bikes, and a space for only bus, right? So here's where we can define something like if you have a license plate, you're either a car or a bus, and you get to go in your appropriate license plate lane. If you have nothing, if you have no license plates, then you're a bike and you get to go down the bike path. Right. So that's kind of our tagged, untagged. We have some definitions about what the types of traffic it is and which lane should go on. You could also say that if you have wheels, you can go down these, and if you don't have wheels, you don't get to pass this, right? So this is defining the different types of traffic on the one medium that's going across, and this is the kind of connectivity and the connectivity and what we define on the switch when we're plugging our device in, be it a switch, a server, a storage array, whatever. We've got to configure these ports with the appropriate VLAN tagging, the access, the untagged traffic. So moving on from there, we've got frame size. I'm sure everyone's heard about that. So let's ask some questions real quick. Jimmy, this is you again. Bam.
Jumbo.
Cool. So a lot of you are using jumbo frames. That's good. Well, it's neither good nor bad. It is a tool, and the tool needs to be used at the appropriate times. So what is, okay, yes, we're done with that. So what is a jumbo frame? What is the MTU? MTU is the maximum transmission unit. By default, it's 1500 bytes. That is the size that can go across the internet. That is the size that Wi-Fi is configured at. That is the size that your local machines all use. By default, everything's 1500 bytes. There is provisions to increase those to 9,000 bytes. And what that means is that when we create a packet and we create a frame and we put it on the wire or on the fiber, we're defining the start and the end of that frame. Excuse me. The start and the end of that frame and how big it is. The analogy I always use when I talk about MTU and jumbo frames is that the standard frame size is a pickup truck, for example, and a jumbo frame is something like a semi truck. So that's why we've got these examples here. And if you carry that forward a little bit and you think about sending something to someone, if I want to send Jeremy a package, I can toss it in the back of the truck, toss it in the car, and I can drive over to his place and hand it to him. And, you know, we use TCP. So I said, hey, Jeremy, here's your package. Thanks for giving me your package. Or I just yeet it into the yard or whatever, right? So that's that 1,500 byte. There's not really any worries I have getting to Jeremy's place or getting anything unloaded from Jeremy or unloaded at Jeremy's place. Whereas if we've got a 9,000 byte MTU, I have to be able to load that truck up. So I need a loading dock, a forklift. I need to be able to turn that around in my yard. And then I actually care about where I'm getting to, where I'm driving. Can I make that turn? Can I get under that bridge? Right. So this road, right? We had that road analogy earlier. This road, my path between Jeremy and myself, has to support the larger vehicle, a larger frame size. And then Jeremy's also got to have a loading dock, a forklift, and a place to turn around. So there's a lot of things that go into enabling MTU size. And we can keep going with that analogy and say that the path between the different pieces needs to support it. And that doesn't really make a difference, right? If this bridge was high enough for me to drive a semi truck under, I can also drive a pickup truck under it. If the switch supports the jumbo frames and those are enabled on the switching, totally fine. You can do that with no detriment. You just have to make sure that the end points, the source and destinations of the two things that are going to talk jumbo frames, once you get the switching set up for that, you have to make sure that the jumbo frames are supported at both end points at the same time, because we don't want a semi truck trying to go up Jeremy's really, really steep driveway and spinning its tires, right? I think you had an issue with that.
Just recently I had to pull a FedEx truck up the road. But yeah, so yeah, and again with the MTUs, from switch to switch, everything needs to have 9,000 MTU turned on, or you're going to get funkiness on the network.
Yep. So just need to know about it. Just need to make sure that we're using it. It involves the network team. It involves also the configuration of your storage array or your ESXi host to make sure that both of those ends are doing the same frame size as we pass traffic. So the one other thing that we do when we talk about frame size, or that frame size implies or matters about, is when we're doing network encapsulation and network overlays and underlays. Fundamentally, what we're doing with that is we are putting our traffic, our normal traffic. I'm going to load up my package to Jeremy in this car, and then I'm going to say, hey, I need to get this car to Jeremy's house. Totally fine. I can drive that all the way there, but I'm using this overlay underlay piece. So really what's happening is I'm driving around my yard, my house, my driveway with my package. And then when I get to the driveway down to the actual road, I'm loading it up on a slightly larger truck to move it from point A to point B. That's how we can then do data center network extensions, how we can do network overlay underlays with either something switch based like a ACI on Cisco, or something server based like an NSX on VMware. That's fundamentally what's happening, is those endpoints, those servers are still talking to each other normally, but we're encapsulating that traffic on a different vehicle to be able to move it back and forth from point A to point B. Anyone have any questions about that one? Complicated concept, trying to make it easy and consumable for you. All right. A little bit of a gear change here. Jimmy, that's you again. Y'all are doing great. Look at these.
Yeah.
Sweet. So I'm actually super impressed. It
Yeah.
does depend. We're talking about, with that one, we're talking about link aggregation. One would think that in general, link aggregation means I get more throughput, right? Because I've got multiple links. Link aggregation is a fun one, along with VLAN tagging. Um, Different vendors have different names for the same things. A trunk is the trunk on Cisco, but it's something else on HP, and a F5 load balancer. They refer to different things differently. Yes. Okay. Whoa, 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 too far. So you'll hear it called teaming, bonding, aggregate Ethernet, interface groups, all of that kind of stuff, right? Ether channel on the Cisco side. We're talking about there's two different pieces that go into that. There is the negotiation. Hey, Jeremy, do you want to use two lanes, two traffics, two links to get our traffic back and forth? You decide yes. I say, hey, I've got this one, this one, and that one, and we have a negotiation about it, and then we call that the path to get from point A to point B. Alternatively, we don't use a negotiation, and we just say turn it on. When the ports come up, put them in a channel, treat them as one. And that's where you'll see on a drawing, you'll see something like this. Here's two links with a little line, the circle around them. That's that port channel. That's that channel group, that aggregate Ethernet. And what we're doing is we're describing that those two physical links, right? Because here's one physical link and here's another physical link, are treated as a logical link. So you can treat that as a single device, a single path. And so the question is, why won't it go faster? If I've got a road with a speed limit of 60 miles an hour, I'm supposed to drive 60 miles an hour down that road. If I add another lane to that road, is the speed limit now 120 miles an hour? No.
No.
Right? So fundamentally, you can only drive down one lane at a time. So you're only going to get 10 gigabits of throughput on that link, even though we've got two 10 gig links put together. What'll happen is you'll get more data to the end at the same speed. So if I've got a web server, a bunch of clients, those clients are going to end up spreading across multiple lanes of traffic, and we'll get an aggregated throughput of up to 20 gigs, up to whatever that channel group builds. But a single set of traffic, a single device from point A to point B can only ever use one lane. So it's only ever going to go at that speed. Mind blowing, I know, right? Let's take a look at some media. So here we go. Here's another fun one. UTP, Unshielded Twisted Pair, has got a couple of different flavors. Honestly, I didn't really know Cat 8 existed until I was putting this slide together. Most of the time, I'm not seeing anything over Cat 6. Cat 6 installed in an environment, and this is primarily what we're using for structured cabling. This is going to be out to the desk is where this is designed for. That Cat 5 cable, that Cat 6 cable is fairly cheap. We run it through the walls, punch it down, use these connectors that have been around since before I was born. We plug them in, and that's how we get our connectivity. Which brings us to our next question for y'all.
Think about this one.
I almost feel like that's kind of a gimme.
Yeah. But it's good to acknowledge it. It's good to acknowledge it. Make sure everybody acknowledges it.
So no, all 10 gig is not created equal. Because we have this concept of 10 gig over Ethernet, this UTP that we just took a look at, 10 gig over Ethernet, 10 gig base T has some requirements that are different than 10 gig over everything else. You can't go as far on that UTP, on that shielded twisted pair, as we can on fiber, as we can on specifically just fiber. And the bigger issue is that 10 gig base T uses a little bit more power than all of the rest of the connections. So when we're buying a switch, this is the one we run into the most. When we're looking at a switch and connectivity that we want for our environment, 10 gig base T is a specialized thing over in the corner that may have a little bit of a lower cost to entry, but I can't do anything else with it. It has to be 10 gig base T and it has to be over UTP, which means that I'm stuck at most with 100 meters for my Cat 6 connectivity over 10 gig base T. 100 meters, it's got to be copper, and I can't do anything else with it because most of the time I don't run copper between my buildings, right? Which brings us to a little bit of history lesson here. We've got LC connectors. This is what we'll see most of the time when we're talking about fiber, is an LC connector like this. Oftentimes the yellow cabling means single mode, and the different colors, orange, aqua, teal, will mean multi-mode fiber. And we'll talk about that fiber here in just a sec. Next to LC, we might see an MPO connector, which, if you look really closely, is the same form factor, but it's got different individual strands of fiber terminated into it. Here's an MPO 8, and there's a 12, and here's a 24. So it's one connector with 24 strands of fiber in it, 12 strands, 8 strands of fiber. And this cable here, this tail, the actual fiber itself, is about the same size, about the same physical dimensions as this cable. That's pretty cool. So you can get a lot more throughput on a single cable with an MPO connector on it. A lot of times what I'll see, or what we see, one of the things we'll see is MPO connector sold as a pre-terminated structure cabling. So you might have your vendor install an MPO connector and then plug in a breakout cable and break it out into that bulkhead connectors, or you plug in the LC. That'll look something like this.
It kind of eliminates the need for the big, huge patch panels that you can have in your data center that you don't really need those as much now with these.
Yeah. Or we might see them as the connector on the individual optics, where we plug the optic into the device and then we plug an MPO cable into it. And this is how we get our 4 lanes of traffic. We use MPO 8, and we've got 8 fibers is 4 pair. So we can have 4 lanes of 10 gig traffic that gets us 40 gig, or 4 lanes of 25 gig traffic that gets us 100 gig off of this MPO connectivity, usually on a QSFP port. So all of these to say, optics and connectivity is important, right? Maybe I've got a QSFP that I'm breaking out into multiple 10 gig lanes, and I'm using each one of those lanes independently. We have to match what we're connecting up on our server side or our storage side to what we're consuming on the switch side. As we get through that, as we drive down that fiber path a little bit more, the size of the fiber inside of the strand is what defines the single mode, multi-mode. Multi-mode's a little wider, a little bigger, thicker. We're talking about micrometers, so just a slim bit thicker. But we're able to bounce different flavors of light, different colors of light down the multi-mode cable, which makes it a little easier, a little cheaper to produce, a little less distance, because we can pass multiple light lengths down it. Whereas on single mode, we've got a single type of light, and we're passing that down the cable, and we're able to push that a little further. The single mode, I believe, is always been glass, actual proper glass, and multi-mode maybe some acrylic or plastic or something with glass. There's been a lot of different flavors of multi-mode and single mode. Single mode's kind of been around forever. A lot of installs between buildings, longer distances, have been single mode fiber, and that just kind of keeps working, right? We don't have to really update anything if we've got a single mode fiber installed. The prices of these optics and everything's coming down. They're moving towards each other. I'm finding single mode optics and multi-mode optics are about the same price these days, or there's at least not that much of a difference between them. You will see orange fiber, OM1, OM2, FDDI, I think.
16.5 micron.
Yeah, that's a weird fiber, actual fiber size. This orange stuff, we can't really do a whole lot with. This is kind of similar to my Cat 6, Cat 5 cabling, where I can't get as far out of it. For everything we're putting inside of a data center, it should at least be OM3 or OM4. At this point, if we're going to run links between them, consider going single mode links between them, because you'll never have to change it. And then look at kind of what the different components of the fiber are. This core is what we're talking about when we're talking about the what is it, 8 to 10 and a half micron to 50 to 100 micron. That's that core size. Hang on one second, I cough. All right. So fiber connectivity, we've got SFP optics. These are the same size, same physical dimensions, and they come into different flavors. There's SFP, SFP plus, SFP 28. Those are the major ones we'll see today. If we're looking at a brand new switch, we're not going to do 10 gig base T, so we're going to get SFP 28 ports in there, which means that a new switch today, if you're buying one, should be 48 ports of 25 gig SFP 28s. I can run 25 gig on there. I can run 10 gig on there. Most of them will have a couple 6 QSFP 28 ports on the end for uplink, so I can do 50 gig or 100 gig. That was the wrong button for me to click. I was trying to mute myself so I could talk. Excuse me. We're looking for the QSFP. That's the same thing. Here's the MPO connector in there. Which brings us to a lot of these. Yeah, a lot of these actually, you can get that breakout cable, right? So we've got the QSFP port. I can configure it. You can configure it on switch side so that it's 4 10 gig links or 4 25 gig links, and then use those independently somewhere else. Plug those into your server, kind of a thing. So it's optics like this, or it's a DAC or a twin axe cable. Usually it's a bit cheaper. It's going to have that same kind of end. It's going to be SFP or a QSFP. And then the big things about twin axe or DAC is that the length matters. Same kind of thing with a 10 gig base T. If we're going 7 meters or higher, then we need active cables. Those active cables need more power. Most of the time, your switch port or your server ports don't supply that kind of power. Which brings us to our rules of thumb for twin axe or 10 gig or 25 gig.
Don't go over 5 meters.
25, 5 meters for twin axe is the stopping point for all of the connectivity. If you want to go over that, you should use optics. And then similarly, if you're going between different devices, so like a Cisco switch to a Juniper switch, we like to use optics there so that each side has its own hardware, its own HCL. I plug my Cisco optics in my Cisco switch, my Juniper optics into my Juniper switch, and everyone's happy, rather than trying to have a Cisco twin axe cable plugged into the Juniper side, and then you call support and Juniper's like, well, that cable sucks, and issues arise. So that's our rules of thumb there. Pretty simple. 5 meters is the important one. After that, if it's weird, use optics. It's basically what it comes down to. So, who is your network team?
A bit of a mix. Almost 50-50.
That does look about the same.
Yeah.
Pretty darn close. I'm surprised.
Yeah.
We're about 50-50 on that one.
Yes.
which is pretty common, I think. Either you're the guy that does it all, or you're the guy that does it all, or you've got some people to do the networking side for you. Yes. So okay. Jeremy, did you have anything on those slides already? On those bits
No,
we
I
went
want to
through?
keep us moving. Yeah,
Yeah.
we covered it.
Okay. You want to do the hypervisor, the storage, or the load balancer?
I think the hypervisor is probably the gonna it's gonna answer a lot of the same questions that the other ones are going to.
Okay. So you want another hypervisor. So super easy. We say, hey, let's add four more hosts to the environment, right? We have this scoping call. We say we want to add some stuff. I say I want this much CPU in it, this much memory in it, some TPM modules, some boot media. Cool. I need 10 gig ports. Give me some 10 gig ports, right? That's all I want. That's all I ask from a server point of view, right? There should be a little bit more that we go into with that, like uh, what kind of port type do we have right now, right? I say I want 10 gig ports on there, and Dell quotes me a server with 10 gig base T ports in it, but I need, well, hell, Jeremy, I don't know. What do we have on the network side, right?
Yeah, exactly. So you need to come up with these are all the questions that you need to ask and answer to give to the network team. Do
Mm-hmm.
you need how many ports per host? Is it 10 gig, 25 gig? Who's going to allocate the IP addressing? SFP plus, SFP 28s. How many connections? What storage? What protocols are you running? All these other fun questions.
Right. And of course, one we don't really harp on very much because it's often kind of a broader question. Do we have space for it? Do we have power for it? Do we have cooling? Important things. Above and beyond that, networking has to do some stuff to get these ports ready for us. And we're going to ask questions such as,
Will they require a port channel? Is this going to be a channelized connection? Are you doing load-based teaming? What VLANs do you need to be allowed on these networks? Is it going to be do you need multiple tagged VLANs? What do you need the native VLAN set to? So that way, when you boot up your machine and you want it to come up in a certain VLAN and get a DHCP address, so that way you can configure it, what do you want that native VLAN to be set to? And how many ports are required? You could end up having, multiple different storage connections. It could end up being two connections for your data with multiple different tagged VLANs and then two storage connections. That's what we need to know.
right? How are we going to build these? What are we going to carve them up on? Do I need to pass iSCSI traffic on my client access ports? Questions to answer, design sessions. One of the things I like to do when I'm building a solution for a customer is answer all of these, draw a picture, right? It takes me a couple of minutes with a whiteboard. We point at all of the pieces, ask questions about all of them, make sure we've got everything done before we actually spend any money. It's way easier to do that work up front than try to fix it later. So in our hypothetical example here, what do we got, Jeremy? What are we connecting to?
Well, I have 8 ports of free on each switch. That allows you to connect up to 16, but so that's what we have. We have SFP 28s and it's a pair of Nexus. So we can do port channels or VPC between the two interfaces if you need it. And I have plenty of 1 gig connections available for your management.
Mm-hmm.
Tell me what you need.
So we said what, three hosts, 4 hosts, with a 4-port network card. So that's what, 12 ports total.
Yeah. So we'll have 4 ports left over on, so that's, we'll have 2 ports left over on each switch when we're done.
Yep. A little more than that, but yeah. And so sometimes we'll compare it to our existing environment and say, hey, our current switching has 2 25 gig uplinks. So I need to, at that point, that's going to answer the question. I'm putting an iSCSI, NFS, whatever, my storage traffic on those same links as I'm doing client traffic. And then maybe I do 2 1 gig links for management, for just the ESXi host management connectivity, right? So this is kind of defining which which kind of config I'm going to need on my network ports and where my traffic is coming from. If we're using iSCSI, we need to make sure we've got the iSCSI A, B networks kind of carved up appropriately, and it's going to dictate our virtual switch config, or either our DV switch or our standard switch, and the port channel config on that. Oftentimes we'll match our existing environment. Sometimes we'll make some changes depending on what we're doing. Do we, are we adding to a cluster, or are we replacing to a cluster and having an opportunity to rebuild some of the environment? We'll do this exercise. We see these 10 port groups are going to exist on the environment. We need to do BMC, baseboard management. We need to do some management of the hypervisor itself, some vMotion, some iSCSI traffic, and then some server client traffic, right? Some client server traffic, I guess. Assign our addressing to them. This is going to kind of drive that. Jeremy, do I have free addresses? Where should I start my addressing? Who owns the addressing? Are we pinging hosts? Are we doing a IPAM device to figure out what our addressing is for the environment? All of those things are appropriate. Take a look at our physical space for the server. Make sure we've got capacity on the PDU. Make sure we've got enough airflow. I don't know if any of you have had server stuff installed in an office space, but a lot of the people in the office space don't like it when that closet starts going.
Sounds like a jet engine.
We didn't talk about that. Yeah.
And while you're in there, it's a good idea to give yourself a rack elevation diagram by the time you're done. So then that way you don't have to remember what it looks like when you're done. You have a picture already. So that's a good thing to do while you're in there.
Yeah. So we do all of that. We do some drawings. Jeremy knows what free ports he's got. We're able to say, hey, you know what? For my host 1, let's plug NIC 0 into the catalyst. Let's plug NIC 1 into the other catalyst. Let's plug NIC 2 into the Nexus, NIC 3 into the Nexus. And then on our second host, we'll plug it into here and plug it into there. Now Jeremy has all of the information he needs. We know where we're plugging this in. He can go configure the 1 gig management ports as an access. We configure the Nexus ports as a trunk port with tagged VLANs and untagged VLANs and native VLAN.
We can also label the ports at that time with the data fill. Now labeling is only lasts as long as the last person who touched it or the last person who moved it. So with labeling, it's always a trust but verify, but it is something that's usable.
So that's kind of what that workflow is going to go like. There's a lot of questions that networking needs to know and answer before we can just configure a port. I can't just like turn it on, plug it in, and let it work, right? There's even that kind of a thing would need some extra work on it.
I think we have enough time to kind of go quickly through the storage.
And the storage or load balancer?
I'll leave it up to you.
I think the load balancer is way more fun.
It is more fun. Okay, let's do it.
Okay, we'll do one more. So we're going to do a load balancer, this one, right? Similar kind of questions. This one's a little bit different in that a load balancer, a network, is kind of a network device, and it's going to participate in some of the routing, right? So where are the clients? What's the servers? How does the app work? There's different designs for a load balancer. I can do a routed, I can do a one arm. Is it a physical device or a virtual device? Do we actually know enough about our application to be able to load balance it? Or are we going to kind of, yeet it in there and then figure it out as we start configuring it and kind of problem solve as we go that way? Most of the time it's the latter one a little bit. So, we got to know these things, and we should have networking present on the design stage, because how we get the traffic, how we get the clients in and through the environment makes a difference. We can have public internet clients, and these two servers are being load balanced, and we then have this conversation with networking and say, hey, do you want to route this? Do you want to do a one arm? How do you want to install it? Many of you have maybe never heard those two terms before, which gives us this, right? So you've got an end user up here on the internet coming in through your /27 or whatever the ISP has given you. They come through your firewall, they hit some sort of network, And then they hit the load balancer, and the load balancer routes down to this other network where our servers live. This routed environment implies that my management, for example, that lives over here also has to come down through the load balancer to get to the environment, right? That's routed. Versus we put it in a one-arm environment where I've got same users coming in, hit the firewall, and then we've got a layer 3 device. The firewall pipes the traffic towards the load balancer, right? That's how the client traffic goes. The load balancer load balances it. And then oftentimes we'll do something like a NAT, a source NAT reply to the server. So what happens is rather than seeing,
it's like a proxy almost.
Yeah,
right?
it proxies the traffic. It terminates the traffic. In this instance, the server itself sees the request from the end user and it says, end user at public internet address 1234 ask for this thing. I'm going to send it back to 1234. Whereas
that could have ramifications for your application, because if your application needs to see the real address of where it's coming from, that's also a determination of how this is deployed.
Yeah, right. So what's the app do? That's that other section of the question, or that's that other piece of the question. Whereas if we're doing a one arm, we're going to bring the traffic in, the end user's asking for 1234, and it's going to come in through the firewall and get natted here. And it's pointed this way, right? We point 80, we point port 80 and 443 to the instance on the load balancer, the VIP on the load balancer. The load balancer then turns around and source nats it again to give to the server. So the server will see, hey, the load balancer asked for this request. And that's where that source destination traffic is going this way. So when the server sees that request with a source of 10 dot something, returns it to the load balancer unnats it, and then sends it back out to 1234 to get to the end user. Two totally different deployments have a big implication on how we're designing the environment. So we have this conversation, we decide what we're going to do. Do you need to add routes to the environment? Do you need to build me a brand new network, Jeremy? I don't know. What do you need? Right? We say, hey, you know what? Let's do this. Let's do a virtual one arm. And then, do you have a network for me? Do you have a VLAN for that one arm to sit in? Do you need to build one? Right? Do we need to plumb this extra VLAN into the vSphere environment so that we can create a port group, so we can plug this load balancer VM into these port groups? Right? All of those then need to get built as well. And let's see. So we're going to use VLAN 26, right? We have to build that as a new one. We build a subnet in there. We make a gateway. We're going to add the VLAN to the ESXi ports. And then, we need to build a new port group, and we need to configure SNAT on the load balancer because we're going to do the one arm deployment mode. And maybe these are things we got to talk about: connectivity, redundancy, right? So, last one for you.
Would you like to know more? We covered this stuff very, very high level. There's actually more to the presentation. We ran out a little bit of time.
Yeah, we skipped a whole section on storage.
Yeah, we skipped a whole section on storage. This is our first run through on the webinar, and
yep, thank you for joining. Thanks for spending an hour with us and letting us chat at you about networking.